So, and as well as it worked 15 minutes ago, it's not working at the moment, unless you can see my screen right now, which I don't think you can.
No, it's just blank. Yeah, because I just saw it a few moments ago.
Yeah, is there a way that you could make me a co-host? I'm wondering if that
Let's see here. Let me see here.
Maybe it's working now.
I wonder. There you go. There you go.
Okay, fantastic. I apologize for the technical difficulties. Well, it's great to be here and sort of back in North Carolina virtually, at least. I'm coming to you from the Akron Zoo today, which is where I'm working. And so would love to have been there in North Carolina. Obviously, I see a lot of familiar names, if not faces, in the list of attendees. And so good to see you all virtually again. Some folks that I worked with when I was at NC State for nearly a decade. So I've been up here in Columbus, Ohio for the last 4 or 5 years now. And my research group is really focused in on trying to come up with solutions to stormwater questions that we have in the Great Lakes region, which do vary quite a bit from North Carolina. But I'm really going to focus in today on bioretention, which I know is a very popular device stormwater control measure there in North Carolina. And I'm secondarily going to really focus on nutrients here because I know, again, that's quite important to y'all. And really going to do this from the laboratory scale starting and then really moving on to the full watershed scale. So just a quick outline, we're going to start with a literature review that we worked on with the folks out at UCLA, looking at bioretention soil media and the design of that media and how that affects performance of these bioretention systems, which I'll quickly outline in just a second. Michelle, are you seeing the screen?
Yes, I can see it.
Okay. All right, fantastic. Just making sure. Some lab work related to compost in bioretention soil media, just share some preliminary results with you there, and then really dive into a couple sort of larger scale projects in the real world. One at a Meijer store, which I know is not a chain in North Carolina, but is a equivalent to a Walmart or a Target sort of super center type thing in the Midwest. And then Blueprint Columbus, which is really a watershed scale approach to green infrastructure installation that the city of Columbus has been working on for the last 10, 15 years. And we've been lucky enough to collaborate with them over the last 7 years on a long-term research project looking at watershed scale impacts of bioretention. So much like North Carolina and the tar PAM and the noose, these pictures probably look somewhat familiar, just in a sort of different shape here, right? This is Lake Erie, the northern coastline of the state of Ohio. And you can see our big driver is similar to yours, and that is eutrophication, fish kills, algal blooms, all the negative consequences caused by excess nutrients in stormwater for both agricultural and urban regions. This is a big driver, particularly because the western tip of this lake is the city of Toledo, where the water supply was closed for about a week in 2014 due to the neurotoxins that were released by the harmful algal blooms in the lake. So one of the approaches to control stormwater is bioretentions. This is my quick bioretention intro slide, and many thanks to Sean Kennedy at NC State for creating this awesome graphic. You can see, for those of you who aren't familiar, it's a planted media filter. So we have an engineered soil here in the middle of the system with a series of drains, typically with gravel surrounding the drains to allow them to function. Typically the water is going to come in, pond on the surface, filter through the soil media where it's treated by plants, microbes, and physical processes as it passes through the filter. So this is really our focus today in this particular talk. And I want to focus in initially on the design of this bioretention soil mix, because it is really critical to both the runoff quantity control. So in other words, how fast the water passes through the filter, what the hydraulic retention time is in the system. So the more sand you have in the mix, the faster the water is going to move through, the higher the hydraulic conductivity. And therefore, typically, the lower the water quality performance, right? So the longer you're able to hold on to the water in in these systems, the better typically, as a rule of thumb, the water quality performance. And one way this is done is through internal water storage. And I know most of y'all in North Carolina are going to be familiar with this term, where we have this upturned elbow in the underdrain, and Bill's group has done a lot of great work. Bill Hunt's group has done a lot of great research over the years on the impacts of this design change, where we're storing water internal to the bioretention media, spurring denitrification, causing improvements in runoff reduction, et cetera. So that's another sort of design that we can make to these systems. But again, what I want to focus in on today initially is really this bioretention soil mix and the impacts of it. So this is, again, work that was done with UCLA, so I want to thank them on this literature review. So you can see here some of the impacts of the different design pieces in bioretention. And really the key factor is what's in the soil blend, okay? That controls all the pollutant removal processes that you see on the right. And generally speaking, as I mentioned, the larger the particle size, the faster is the infiltration, but the worse is the water quality improvements that you see in the system. So other things that are often included in bioretention soil mix, apart from sand, silt, and clay, include some fraction of organic matter. And this really varies based on the particular location or jurisdiction that is putting together these bioretention soil mix recommendations. Okay, so this is our standard mix in the state of Ohio. Those of you who are familiar with the one in North Carolina, it looks very, very similar, with the exception of the fact that we use compost as our organic matter, which I'll talk about in just a second. And it's 3 to 5% of the mix by mass, which results in up to about 1/5 of the mix of the soil blend by volume. So this is quite a large compost content. And so one of the things that we've been working on recently is some laboratory studies that I'll get to in just a bit to look at how that compost content affects water quality performance. Before I get there, I want to just touch on a few things in this literature review that are really helpful. We pulled together data from a number of different jurisdictions across the country and the broader world for that matter. And you can see here just all of the different factors that go into the design of these bioretention soil mixes, maximum P contents, pH, textural classification of the soil, et cetera. But the one I want to really touch on here is this compost by volume. You can see a massive difference across the various jurisdictions from essentially zero in a number of countries, Germany and Australia, up to 20-25% by volume. And so this is, I think, perhaps the most important factor in the mix is getting this right. And so I'm going to try to hone in on what we think is best here in just a bit for that compost content. But before I do that, I also want to mention in this lit review, we went beyond just looking at standard bioretention media and looked at different things that you could actually amend bioretention media with. Typically, waste products, industrial byproducts, agricultural products like coconut coir that are available and cheap that can be added to bioretention media to improve performance. So we looked at this for heavy metals and hydrocarbons and as you can see here, nutrients as well. And we're essentially able to, because there's actually been a number of lab studies that have been done on amendments at this point, essentially able to come up with recommendations in this work. Look at, do you essentially have concern about dissolved pollutants in your watershed? Are they nutrients? Are they metals? Pathogens?
Let's see, I can't get a volume here.
Etc.
Excuse me. Is there any way you can mute your mic?
Meeting.
Hello, I'm so sorry. I don't know who's talking about their volume. If you could please mute your mic, that would be wonderful. I think that's Mr. Edwards. I think I just tried to mute him. Okay, I just requested for him to be muted, so I think you should be good now, Ryan. I'm so sorry about that.
No, it's all good. It's all good. So essentially what we've come up with here is a list of potential amendments as a function of your particular pollutant of interest. And so you can see those here. We also tried to do some cost analyses on these in this particular work. So I'll just mention, I'll put my contact information up on the question slide, and I'm more than happy to take emails if you want any of this work. I'm obviously going to just touch on the 10,000 foot view here today. But, so these are a list of kind of the typical best products that can be added to bioretention media as a function of your particular pollutant of interest. but there's still a lot of need to optimize these, particularly at field scale. Most of these tests were done in the laboratory at the column scale, which I'll talk about here in just a second. So in Ohio, there's a huge driver to get it right, to get this mix right, because we are implementing bioretention by the many hundreds. So this is an example in Columbus, where I live, city of 1.5 million people, with a lot of historical development. And I'll talk about some sanitary sewer overflow problems later in the presentation, which are driving a lot of these retrofits. But you can see the neighborhoods here that are in green. These are all neighborhoods that are slated to get, each one of them, many hundreds of bioretention cells retrofitted into existing development. So obviously there's really, it's really key to try to get our mix as dialed in as we can, to make sure that we're getting the most sort of bang for the buck. So the next scale we've been working at is really this laboratory column experiment scale, where we've been building lab columns, soil blends there in the pipes and amounts in our bioretention media, and comparing those against sand filter controls. And we've been doing this in sort of replicated column experiments where we have 21 basically large trash cans that we've made into soil filter columns. We've not planted them, so I'll mention that. We're just looking at leaching of nutrients and metals and from the soil blends themselves. So we've looked at two different types of organic matter: woody waste compost and standard yard waste compost, both of which were sourced from a certified composting facility. And we looked at different amounts of organic matter, 1, 2, and 3 parts out of essentially a 10-part mixture of sand, topsoil, and organic matter. So a variety of percent by volume, essentially. We put 1 year of rainfall through these columns, about 60 storm events that we simulated over a half a year. So it is accelerated testing, and sampled for, sampled in 11 of those, trying to get rid of that video, all right. Sampled in 11 of those simulated runoff events. So you can see our testing schedule here, basically putting 3 storms a week, about 2 inches of rainfall through each of the 21 columns. Obviously, this is laboratory experiment, so it's simulated runoff. And you can see the weeks here where we're simulating storms. I did give the graduate student Christmas off. I'm a nice advisor. So she did really great work, though, and you can see in certain weeks sampled on certain days, for a total of 11 samples across the 21 columns. So, roughly 250 water quality data points that I'm about to show you in each of these graphics. So this is an example. This is one of the labile forms of nitrogen. This is an aqueous phase. Nitrate is dissolved in the water typically. This is yard waste compost. The first storm event that we simulated is here on the left, and the 60th storm event is out here on the right. So what you can see is this incredibly high leaching of nitrite in the first few storm events. This is 100 milligrams per liter. For those of you who are familiar with urban stormwater, typical nitrite is maybe a half a milligram per liter. So this is extremely hot with nutrients. This yard waste compost leaches the nutrients in those first few events, and then eventually does decline, but declines to actually relatively high. You can't really see the scale here, but actually relatively high concentrations even after 1 year of simulated runoff. Compare this to the woody waste compost, and you can see the difference here in the scale. This woody waste compost for the same pollutant, about 1/100th the leaching. So clearly one of the things that we've taken away is that yard waste compost is just we think absolutely a no-go. The woody waste compost has higher carbon and nitrogen ratio, and it just does not leach as much nutrients because of that. And so you can see here we're getting down to reasonable effluent concentrations out of these columns, down below a half a milligram per liter, which would indicate some treatment essentially in these systems. Dissolved phosphorus is a big driver here in Ohio because of the algal blooms that I mentioned earlier. And you can see here the different parts, organic matter, 1, 2, and 3. So the further you go on the right in these graphics, the more compost there is. And generally, you can see that that's directly related to the effluent concentration from these two types of compost: woody waste on the top and yard waste on the bottom. Again, yard waste releasing higher effluent concentrations than woody waste. Again, speaking to the use of woody waste compost is the way to go. And I know in North Carolina, you guys tend to use pine bark fines in your bioretention mix, which would be very similar to this woody waste compost that I'm referring to here. So total phosphorus in the effluent here for woody waste, you can see again, very hot in the first few storm events and then an exponential decay. So the same trends that we saw for nitrogen, and similarly for total suspended solids. Again, you've got that loose filter media mix when you first install it. And so you do tend to get actually fairly dirty effluent in the first few events, and then it levels off to really consistent performance as the soil consolidates over that first few rainfall events after construction. Similar performance for 2 parts organic matter. The first graphic was 1 part organic matter, 1 part compost. This is 2 parts compost and 3 parts compost. So you can see all 3 of them have very similar trends for total suspended solids in the effluent from these columns in the laboratory. So, and you can see here just visually the effluent as well. This is our first sample from the first storm event that was run through the column, and this is the 60th sample that was taken, at the end of the year of simulated runoff, and you can visually see the difference in effluent turbidity there for sure. All right, so soil mix recommendations. I think this is obviously preliminary data at this point, so not the end all be all at this point, but we really are working with our version of NCDEQ to try to update our bioretention soil mix designs as a result of these first 2 pieces that I've shared with you. So obviously woody waste in lieu of yard waste is a clear takeaway here. Reducing the volume of organic matter, I think is really important. Watching that Malic 3 phosphorus recommendation, I didn't really talk about that at all, but the state of North Carolina includes this in their bioretention soil mix recommendations. Making sure that's low enough to prevent phosphorus leaching is really important, and we have that same guidance here in Ohio. And then really the question that we're going around and around with our version of NCDEQ, which is Ohio EPA, is do we even need compost in this mix? Do we need organic matter at all? There's plenty of dissolved organic matter coming in the stormwater, and certainly lots of nutrients coming in the stormwater as well that are getting focused into these bioretention systems. And so we're asking the question, kind of going back to the drawing board and thinking about, do we actually need organic matter in our blends at all? Don't know the answer to that yet, but that's something that we're sort of beating around. Want to move more to the field scale here and think about a traditional big box store. This is the Meijer store that we're working with. It looks very much like a Walmart from the 10,000 foot view. And we've had a long relationship with Meijer. This is in Reynoldsburg, which is an eastern suburb of Columbus, but we're working with them in Traverse City up in Michigan at the moment as well. At this site, you can see the sea of parking here, right? Just massive parking lot, very similar to any big box store you might have been at, designed for the Black Friday type of day, although I'm sure the parking on Black Friday is no longer as bad as it used to be with Amazon and the like. But massive parking lot, et cetera. And so the idea was to essentially cordon off a couple of the inlets here and retrofit in green infrastructure. So we have a bioretention cell that was retrofitted in the eastern part of the parking lot, and adjacent to that, a 9-stall permeable pavement parking area. And really, we're trying to monitor and compare the two in terms of functionality, because Meijer's really looking to build out green infrastructure at all of their stores. And so they were trying to get some initial data and feedback on what works and what doesn't. So I'll mention that the drainage areas kind of go from north to south here from the store, to these BMPs, as you can see in the pictures here. So the way that we monitored this site is we had an on-site rain gauge, which is shown in blue. I'll show you the soil cores that we took at this location in orange in this grassy area to look at the soil profile. Bioretention cell in this, and so we monitored at each of these dark blue locations, monitored runoff hydrology in the sewer. So we have a control watershed here, which is a Max and Irma's. This is essentially an eatery, a restaurant. And a green area, this is the watershed for the bioretention cell, and the watershed for the permeable pavement. And I'll just mention, this watershed for the permeable pavement is 27 times the size of the permeable pavement, and that will come into impact some of the things that I will talk about in just a second. So this was done using a paired watershed design where we have a control watershed, which is this Max and Irma's, where we're not installing any BMPs. And then we have treatment watersheds, right, where we are installing BMP. So we monitor these 3 watersheds before BMP construction, and I'll show you in just a second. We monitored for about a year prior to construction, and then we're actually continuing to monitor now, but when these data were put together, it was about 2 years of data post BMP implementation. And using this paired watershed design, you can quite nicely look at, okay, the control's not going to have any change from pre to post. And you can use the statistical design to then tease out how much impact your treatment has, okay? And the gist of this, there's a lot of fancy words on this slide, but let me just break it down to the gist of this, is you plot the amount of runoff from the treatment watersheds versus the amount of runoff for the control watersheds, okay? You do this for pre-BMP implementation and post-BMP implementation, and then you run a linear regression through those plots, okay? If you see a substantial disparity between those 2 lines, that suggests there's been a treatment effect, i.e. that your BMP is having some impact, in this case on runoff hydrology, okay? If these lines overlap, that means that what you did had no effect, okay? Statistically, there's no impact of that BMP that you've implemented on hydrology in this case, okay? So the site soil conditions, I just want to mention briefly because they are going to come into impact some of the findings. We had an A horizon up to the very top, but we had a slightly organic layer down to about 18 inches deep. And then below that, a really stiff clay soil with the water table at about 5 feet below ground surface. You can see some of the pictures here of one of the soil auger that we did out on site. Site characteristics, just briefly, just want to mention here, there was internal water storage, which I mentioned earlier, that was implemented in both the permeable pavement and the bioretention cell. And this run-on ratio for the permeable pavement is insanely high. So we were trying to really push the envelope here and sort of see how fast the system failed, okay, in terms of clogging of that permeable pavement surface. I should mention, if I can go back a couple of slides here, I should mention that we monitored downstream of this permeable pavement as well in a catch basin here. So we were able to look at the combined effects of the bioretention and permeable pavement. And we've called that LID, or low impact development, in this 3rd column. And I'll mention those results in just a second. So project timeline, we monitored for about, we're actually still monitoring, so we've got about 6 years of data now, but at the time we had a year of pre-construction data. All the BMPs were built in November of 2017, and then post-construction treatment period data collection over 20 months. Okay, so there's a lot of data on one graphic, and I'll walk you through it slowly here. So the first column is the bioretention cells, singular, excuse me. Permeable pavement is in the second column, and the third column is our combination of the two, what we're calling LID. Okay, the top row is runoff volume, and the bottom row is peak flow, right? Peak flow. Each of the dots is a separate storm event that we monitored. The solid dots are before BMP implementation. The open dots are after BMP implementation, okay? So for the bioretention cell, you can see quite clearly, here's our linear regression before, linear regression after. There's quite a bit of separation, so that does suggest a significant difference from pre to post for runoff depth, or runoff volume, excuse me. And the same trend for peak flow mitigation as well. So the bioretention cell on average was working super well. In fact, we were concerned better than we would expect, given the super clay soils that I mentioned, which are characteristic of much of Ohio, I might add, and are very similar to sort of the Piedmont clay soils that are typical in North Carolina. So this sort of runoff reduction here struck us as, wow, this is really, really high. What's going on? Okay, so I'll just mention that briefly. The permeable pavement, as you can see, you're like, hey, Ryan, where's the second line? Well, in fact, the second line, that dashed line that you see here, is tucked underneath the solid line, meaning that we actually saw no impact whatsoever of that permeable pavement. So I want to make that point. I know this talk is not about permeable pavement, but the run-on ratio for permeable pavement is extremely important. This one was 27.6 to 1, as I mentioned, 27 parts impermeable asphalt to 1 part permeable pavement. And essentially within the first month, the system was completely clogged, and we could not, over the 20-month monitoring period, tell that it was even there, right? It was acting hydrologically similar to the typical asphalt parking lot, okay? So that run-on ratio is critically important. I'll come back to that in just a second. All right, so I want to dive deeper into the bioretention performance. I mentioned 83% runoff reduction. That seemed kind of unbelievable given the stiff clay underlying soil. So I want to dive a little deeper into that. These are data internal to the bioretention soil mix in this system, okay? There's 36 inches of bioretention soil mix. So you can see a big storm event here, right? The water ponds up within the system, no surprise there. The rain kind of tails off, so the water level drops, right? The underdrain is here at this red line. So, you know, water drains out very quickly when the water level is above the underdrain. No surprise at all, okay? Once the water level gets below the invert of the underdrain at 12 inches, this drawdown of water is all controlled by the underlying soil, essentially, okay? And you can see this very steep decay until we get to this point, right? And then a very different behavior, kind of linear behavior rather than exponential, at a 3.5 inch ponding depth. And I just show a couple of storms here, and you can see the exact same behavior, this exact same critical point at 3.5 inches, okay? And so that led us to kind of think about what would cause this break point, essentially, in the rate at which water is leaving the bottom of this bioretention cell, is infiltrating into the underlying soil, is essentially what's controlling this rate of water decay, okay? So we went back and we really kind of delved through a lot of our construction pictures, and this was the one that really told the story, okay? So you can see we're scarifying the underlying soil. This is the native clay soil underneath this particular facility as it's being built. This is our outlet structure, the existing catch basin that we're using as an overflow. You can see they're cutting in the hole for the underdrain, the upturned elbow in the underdrain here, all right? And what you might note is all of this gravel underneath the existing curb and gutter, okay? Gravel, open graded stones, often used as a base force to support curb and gutter, right? And in this case, right, that was existing in this particular system. So what we think is happening here is that we're getting about actual storage of about 3.5 inches of water in this scarified soil, okay? And then once we pond above that, the water is finding the path of least resistance into this gravel. It's essentially bypassing our underdrain because of the internal water storage zone, right, being set 12 inches above the bottom of the soil. It's finding this path of least resistance in this gravel, and it's essentially causing what's called the urban karst effect. This urban karst is the idea that all of the sewer pipes that we install are bedded in gravel. A lot of the infrastructure underground is actually quite porous, right? And so if we don't collect these internal water level data within bioretention, we just believe like, hey, we got 83% runoff reduction. That's great, super great, right? But in this case, what's actually happening is this really steep curve is the water dewatering out into that gravel that then beds the pipe from this this inlet location to the next one to the west. And so the water is essentially running along the outside of the sewer, and then we don't know where it's going, right? But it probably is not actual runoff reduction, right? The only runoff reduction that we know for sure is occurring is below this 3.5 inch elevation. So I want to make that point that I really think things like anti-seep collars and impermeable membranes in cases like this, where we're up against existing infrastructure and retrofitting in new bioretention systems, are really critical to avoiding things like erosion in places where we really don't want erosion to occur. So this is something we've been thinking a lot about in bioretention design guidance here in Ohio, is trying to prevent this from occurring and really getting the infiltration into the underlying soil that we desire out of these systems. So takeaways, again, runoff reduction, peak flow look great on the 10,000 foot view, but the problem here is that those preferential pathways along nearby infrastructure, and I think it's something that we've seen not only at this site, but several other sites that we've monitored in the field. And so I just want to pass that along as a real takeaway of some of the things that we've done. If you're a designer, this is really key. That run-on ratio and permeable pavement is directly related to maintenance interval and maintenance onerousness. And so please reduce that as much as possible. All right, last 10 minutes here, I want to spend really looking at our watershed scale projects. So going to the largest scale of what we're working on. This is, again, seven-year-long research project in collaboration with the city of Columbus. There are a number of combined and sanitary sewer overflows that go out into the Olentangy River. For those of you all who have been to Columbus, this is Ohio State University's basketball arena here. And so you can see these are, in direct impact to high density urban populations. So a lot of our problems are actually old sewers. They are not combined sewers. A lot of the issues are actually with sanitary sewer overflows, particularly in neighborhoods that have sewer systems that are 80, 90, 100 years old, where they have cracked pipes and you get infiltration and inflow and basically water moving from the storm sewer into the sanitary sewer through that urban karst effect that I just mentioned, right? An interconnectivity between storm and sanitary sewers, even though they are separate sewer systems. And what that causes, right, as the stormwater gets in is overloading of the sanitary network. And then, you can kind of do the math from there. Gross things happen at that point. So the city of Columbus got sued by the US EPA for violating their NPDES permit. And so they've gone through the consent decree process. And part of that was really looking at gray solutions to this problem. So basically digging three large underground SSO tunnels, two SSO tunnels and one CSO tunnel. And then the alternative was kind of green infrastructure solutions along with three other pillars, which I'll mention in just a second, with the goal of reducing infiltration and inflow between the sanitary and storm sewer by 30%, okay, overall across the area where these SSOs are occurring. So basically a 10-year level of service, eliminating SSOs up to a 10-year level of service, I believe is the goal. And this is a $1.7 billion with the B dollar capital project over a 30-year period. The gray solution was a $1.6 billion solution. Of course, these costs with inflation, I'm sure, are quite different today than they were when these data were put together about 5 years ago. But the city ended up choosing the green solutions because of a lot of the co-benefits that can be provided and some of the things that we are monitoring, which includes things like improvements in property value, habitat benefits, and other co-benefits. So they went ahead with what's called this Blueprint Columbus program. And that has resulted in retrofits of thousands of BMPs across the city, and there's tens of thousands more coming in the coming years. And I've already shown you this graphic. You've seen this, and these are the neighborhoods. There's actually several more that are being retrofitted or are planned to be retrofitted with primarily bioretention. We're working in Clintonville, which is a neighborhood immediately north. Campus is right about here. It's about 2 miles north of campus, so quite convenient for our work. The four pillars of Blueprint Columbus are shown here. So green infrastructure is what goes in first. You can see a bioretention bump out here along a residential street. There are about 500 of these that have been implemented in the Clintonville neighborhood in about a 2 square mile area, so quite dense implementation of green infrastructure. Downspout redirection, so basically they're taking downspouts that would have gone down into foundation drains and taking them out instead to the lawn and eventually out to the curb and into the green infrastructure. They're installing sump pumps, so they're actually working in residential houses with homeowners to install sump pumps to get that water out to the green infrastructure. But the main thing is the sewer lateral lining. So the sanitary sewer laterals from the houses to the mains out in the street are where much of the leakage is occurring, where much of the infiltration and inflow of stormwater that's infiltrating through the lawn is getting into the sanitary sewer. And so they're going in and slip lining all of the sewer laterals in these neighborhoods. That's, as you can imagine, quite a process. So our research over the last 7 years, and it's coming to an end, unfortunately, this year, has been really over 5 areas that you can see here. I'm going to focus in on the stormwater pieces, but I'm happy to take questions on the latter 3 if you're interested. So we're doing some social science work, habitat work, particularly with birds and insects, and looking with an economist at property values in this neighborhood where stormwater retrofits have been applied out in front of people's houses versus Columbus in general. So our study, just moving through this quickly because we're running out of time, is using a control watershed in the same neighborhood, this watershed called Beechwold, to compare against 3 other watersheds, Indian Springs, Cook Glenmont here, and Blenheim down here, which are outlined in orange, which have large-scale BMP implementation. So Indian Springs, I think, has about 75 bioretention cells that have been built in about a 75-acre watershed. Cook Glenmont has 3 very large regional basins that have been built in this part of the neighborhood. And then Blenheim has about 200 bioretention cells in an 8 city block area. So massive, really high density implementation of green infrastructure here. So we're kind of comparing kind of low density green infrastructure here, moderate to high density, and seeing what effects we can see at the watershed scale. So our monitoring is actually all at the sewer outfalls. So you can see the red dots here. These are the sewer outfalls out to the streams that these respective watersheds drain through the storm sewers to, okay? And we've been using the same paired watershed approach where we have about a year or 2 of data before the BMPs were implemented. And then, and I'll show you that on the next slide if I can get it to advance. So we have about a year to a year and a half, depending on the watershed, of data, as you can see here. Before the green infrastructure was installed. We then have the green infrastructure being constructed, and then after that, a post-green infrastructure period. You can see one of the bioretention facilities here, and the number of events monitored down here. And then another construction phase wherein the other 3 pillars, the downspout redirection, the sewer lateral lining, and the sump pump installation is done by contractors. So again, we're looking at the kind of the totality of all of these solutions by comparing pre to post green infrastructure to what we call post AI squared, which is post all infrastructure implemented, okay? Period. So this period, we don't have a lot of data in yet. We're actually still collecting data in this period. So I'm not going to say much about this yet. We have a lot of good data comparing at the watershed scale pre to post GI, and that's where I'll focus these next few slides. So this is one of the treatment watersheds. This is Indian Springs, looking again at the kind of linear regressions that I showed you for the Meyer store. Pre-green infrastructure is here in gray. That's our trend line for, this is peak flow rate in this case, okay? Post-green infrastructure is in this mustard yellow color. So you can see that we are having an impact. We're decreasing the slope of the average peak flow that's been observed for a given rainfall event. And so essentially we are seeing peak flow mitigation from these bioretention systems that have been built. And in this particular watershed, there's also some permeable pavement, I should add. And then when we come in and we add these other 3 parts of the all infrastructure implemented or post blueprint phase, this darker orange color, right? We have redirected downspouts out to the green infrastructure. It's out of the sanitary sewer, which is desirable, but again, adds more hydraulic loading to the green stormwater infrastructure. So what you can see is that essentially you see this a new linear trend that actually shows higher peak flow rates or slightly higher. They're actually not statistically different, but slightly higher peak flow rates than what was in water prior to blueprint. And this is the goal of this no impact, is to return hydrology across those 4 pillars to what it was prior to the blueprint project, while also controlling sanitary sewer overflows. It's a very complex
I think we lost his connection. Let's see if he tags back on. I know he was just having a couple of spotty. Can you hear me, Brian?
I can, yeah.
Okay, yeah, we lost you for a little while there. We just had throughout your presentation, we just had a couple of little spots where it was spotty. So
I'm so sorry about that.
No, you're fine. So okay, let me shut up and let you continue.
Yeah, where did you lose me? Just here?
Yes.
Okay, I apologize for that. So hopefully you can hear me. So the thing I was saying here is that we've seen about 70% reduction in TSS at the watershed scale by these green infrastructure facilities that have been installed. So this is just with the bioretention facilities in these 2 parts of the neighborhood, Cook Glenmont and Indian Springs. What's interesting about these findings is that this percentage nearly matches in both cases the sewer shed imperviousness that's treated by the green infrastructure. So in other words, if you're planning for total suspended solids removal in an existing watershed that doesn't have much stormwater control, it's an old neighborhood essentially. If you treat 65% of the sewer shed imperviousness, we expect that your TSS concentration reductions are going to be in that same neck of the woods, okay? All right, in terms of heavy metals, this is lead. This is one example of many heavy metals that we've monitored. You can see this is our control watershed across all the data we've collected over 5-6 years at this point. Blenheim, one of the treatment watersheds, pre versus post green infrastructure. Again, pre versus post green infrastructure in Cook-Glenmont, pre versus post green infrastructure versus post blueprint in Indian Springs. We had enough data here to sort of plot this for all of the infrastructure being implemented. And what you can see is general decreases, right? Kind of following the trends of total suspended solids, we're also seeing across the heavy metals, and that makes sense because heavy metals are often bound to sediment. Where we really haven't seen much improvement, to be honest, is nitrogen. You can see that here, just really, unfortunately, no improvement whatsoever. None of these bioretention facilities have internal water storage, so that could be part of it. Obviously improvements in bioretention soil mix and the things I talked about early in this talk would be another place to spend some time and some thought contemplating ways that we might be able to improve this at the watershed scale. We are seeing phosphorus reduction, as you can see here, very similar plots to the previous plots where we're seeing improvements of sort of 35 to 60% in that range at the watershed scale. So I think broadly speaking, really exciting results here. This is the first time that I know of at least in the upper Midwest, where we as a research community have done work at this scale where we're looking at, watersheds that are up to 200 acres in size, and we're actually seeing an impact, right, of the retrofits that we're doing of stormwater controls as that storm sewer is draining out to the receiving water body. So I think that really speaks to the fact that what we know at the site scale and what Bill Hunt's group's been responsible for doing a lot of research on and others across the country, we know that these BMPs work at the site scale, right? But I think this is one of the first efforts to really look at, okay, across a watershed, if you really go nuts, right, and you implement a ton of these facilities, what can you see? And our initial results, with the notable exception of nitrogen, are very promising. So I'm going to kind of wrap up here and hopefully leave some time for questions. Really, I think there's a lot more work to be done on bioretention media design, particularly in the realm of questions around organic matter, whether it's needed, and also what amendments can be used, things like iron filings for phosphorus reduction or other targeted media designs that can be built out from kind of the standard bioretention soil mixes that are so common in each of our states and municipalities' design guidance. At the watershed scale, we're really seeing impacts, right? Bioretention does alter the runoff hydrology at site scale, at larger watershed scales up to like the 200 acre that I mentioned that we've monitored here in Ohio. And so I think that's exciting news. Some of the places where we still have problems are those dissolved pollutants. So a lot of the forms of nitrogen still are really tough, and we do not see improvements at this point at the watershed scale, particularly in nitrogen. So I think there are still certainly questions and additional engineering and soils evaluations that need to be done to truly kind of peel the onion back and understand what's at the core of the problem. So with that, I'll leave you with a couple of slides of my students doing the column studies in the lab, and hopefully I've left some time for questions. Again, I have my contact information up here. If you want more information on any of these topics, I'm more than happy to pass that along to you. We're also on Twitter, should you be so inclined to tweet. You can follow us there and get more information every now and again on what we're up to. So yeah, thank you very much.
Thanks so much, Ryan. We do have some questions, and I'm going to start from the top. So the first question was, or is, what was the source of the water that you used in the column experiments?
Yeah, good question. So the source of the water in the column experiments was pure tap water, straight out of the city of Columbus, water treatment plant, drinking water treatment plant. So we did not spike it with nutrients, sediment, metals. We were purely running tap water through the column and measuring effluent water quality. We did share the data, but we did measure the quality of the tap water. And as you might imagine, it's very low nutrient content, very low metals content, and at essentially below detection limits and concentrations.
Okay. Next question. We have access to large amounts of organic material that has been essentially sterilized by high heat composting. How would the lack of biological activity affect performance?
Good question. So certainly if you sterilize the compost, the biological is not going to be there initially.
I'm
So
sorry,
the
Ryan. You may want to start over, Ryan, because we're losing your connection.
Is going to naturally kind of
Hey, Ryan, I'm so sorry.
lose me again.
Yeah, we lost the whole question
Right.
answer. I'm so sorry.
Yeah, I'm gonna, but I'm not sharing. So, um,
and then someone, Amy suggested that you may
Also-
turn off your video, so maybe that'll kind of help too.
compost that has been sterilized.
I'm sorry, Ryan.
Do that.
Okay.
All right. Hopefully you
Maybe I
can hear me
you
better. Or can you, I apologize, guys. Can you hear me at all?
Now we can
No?
hear you.
Okay. Let me try again. I apologize. I'm not in my office, as you might. Um, so the sti-
Hey, Ryan, I'm so sorry. I know we're having technical difficulties here. So what I want to do is continue to have you to repeat what you're saying.
Okay.
What probably will be best is maybe that I email you these questions and I can see who actually asked every last one of the questions because I have their emails that are
Sure.
signed up. So maybe I can email these to you. You can give us the response. And that way we won't
Yeah.
put you through constantly repeating yourself and then us having
Yeah.
the technical
I'm
difficulties.
happy. I'm happy to do that, Michelle. Absolutely.
Okay. Okay, perfect. Let me just make sure I have everybody's question here. And so I'll get everybody's question. I'll email those to you and then we'll just kind of go from there. But Ryan, I really just want to thank you so much for taking time out of your busy schedule to assist us in this webinar. And it was very interesting. And so we really thank you. And so I wanted to let everybody else know too, just about our September 21st webinar. Stacy Webb-Finken will be speaking about prioritizing natural and nature-based features to increase resilience in our coastal communities. So you'll probably be getting some marketing material from me regarding that. And Ryan, again, thank you so much. And I appreciate everything, your time today. So you guys have a wonderful rest of the day. And Ryan, do you have anything else you want to add?
Yeah.
And we're having technical difficulties again. So guys, I'm so sorry. So we'll just go ahead and conclude this. And you guys, thank you so much for tuning in once again. And you guys have a wonderful rest of the day. Oh, and the link is below for the PDH. I think everybody got that. So.